Do quantum androids dream of electric cats? Certainly humans dream of quantum cats all the time. If I had a fully automated quantum laboratory, is it going to get hung up on the interpretation of quantum mechanics? Does it care? Maybe it'll get to the point where it can't understand classical mechanics after a while. There's a huge push to build so-called self-driving laboratories. And everything runs in a completely automated fashion. The AI looks at the measurement results, studies these statistics, figure out what's happening, and then adjusts the experiment for the next trial. And you ask yourself, where is the observer in that picture? There's no human there. The human may never need to be in the loop. The little t, the real number t, is not time. It's just a mathematical trick to represent the relationship between coincidences. And what we regard as time is some abstraction based on the fact that things change locally. This is the idea behind general relativity. So general relativity takes it to the extreme. Not only is little t physically meaningless, x, y, and z are too. The spatial coordinates, what matters, are all the coincidences between the physical events. Quantum mechanics came as the biggest shock. When it finally hit me what the theory was saying about the world, I found it deeply disturbing. It begins to raise questions between subjectivity and objectivity, between what Thomas Nagel called the view from nowhere and what I like to call the view from somewhere. When it finally dawned on me what machine learning was all about, that what's sitting between our ears is a machine, the physical device used to compress experience into forms that make it easy for us to respond to the world and control the world. Once you get the message of machine learning, all the physics begins to look very different. In fact, the notion of truth becomes problematic. It already was problematic. You could imagine some machine evolving in a region of the universe where instead of things changing on milliseconds, change on nanoseconds. What sort of universe does that machine see? What sort of laws of physics does it describe? Would we be ever able to communicate with it? Will we even see it? Would we ever talk to it? Almost certainly not. The kinds of things we learn depend on how we're embodied.
If you had to summarize your life's mission in one sentence, what would that sentence be?
It's all about making sense, I suppose. Does it make sense? Is it all just random, or is there some deep structure to experience?
Professor Milburn, you are a professor of physics and astronomy and honorary professor of physics and astronomy in the University of Sussex.
That's right.
Tell us a little bit about yourself and your area of expertise.
Sure. So my main area of expertise is quantum physics of various kinds. Initially quantum optics, but eventually moving into quantum computing and quantum information. For many years, I was a professor at the University of Queensland in Brisbane in Australia, where I ran the Australian Research Council Centre for Engineered Quantum Systems. But then I left and moved to the UK 2 or 3 years ago. And here I have a honorary position here at the University of Sussex in physics, and I have a part-time position with the National Quantum Computing Centre at Rutherford Appleton Laboratory in Oxfordshire.
And what made you initially get interested in this area of work?
Yes, well, it's a long time ago now, but I've always been interested in physics and mathematics since I was 13 or 14, and became very interested in chemistry and mathematics and physics. I did an undergraduate degree in physics at Griffith University in Brisbane. And then in my final year, I met one of the pioneers of quantum optics, Dan Walls, who was visiting and gave a fascinating seminar on the subject. Perhaps a little bit later we can discuss what quantum optics is. So I decided to go and do a PhD with him. At that time, he was in New Zealand. It was a major center for quantum optics. He was a student of Roy Glauber, the founder of the field, who later went on to win a Nobel Prize for that field. So I did a PhD with Dan Walls, and that was my introduction to quantum optics and eventually more general aspects of quantum physics.
What is quantum physics?
Quantum physics is a way of describing the world that is very different from the way that we describe the world based on the laws of Isaac Newton or the laws of electromagnetism as developed by Maxwell, or indeed the laws of special relativity invented by Albert Einstein. It was forced upon us in the early part of the 20th century when it became clear that there were ways of acting on the world that produced results that couldn't be described by the physics of Newton, Maxwell, and Einstein. And so over a period of 20 or 30 years, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger discovered new rules to explain the experiments that were upsetting physics in the early part of the 20th century. So quantum physics are new rules for describing how the way we intervene in the world changes experimental outcomes.
So what did Schrödinger, Niels Bohr, Einstein, Heisenberg, what did they find out that broke the previous paradigm of
Okay,
physics?
so we can start with Niels Bohr, who by that point, when he was thinking about these things, it was postulated that the world was made of atoms, and the atoms had an internal structure. They had a positive nuclear core with negative electrons orbiting them. And when they got hot, they would emit light of only very particular frequencies. And correspondingly, they would only absorb light of very particular frequencies. And that was a bit puzzling from the point of view of classical electromagnetism. An electron being accelerated in a circular orbit should emit radiation at many frequencies, not just one. So that was Niels Bohr's contribution, was to come up with some phenomenological rules that would explain why light was emitted or absorbed only at special frequencies by atoms. About the same time, it was discovered that if you look at how hot matter radiates light, you discover that the classical mechanics predicts that it should in fact produce an infinite amount of energy, which it clearly doesn't. Nobody turns on the radiator and is vaporized instantly. And so trying to apply the laws of Isaac Newton and Maxwell to radiation gave the wrong results. And Max Planck realized, using an idea similar in some ways to what Niels Bohr used, that he could get the correct formula. And that basic idea was an oscillator, such as an electron orbiting a positive nuclear core, or an electron just executing simple harmonic motion, couldn't have any energy that it liked, but had to have very particular energy, so-called quantized energy levels. And it would only emit and absorb radiation when it made a transition between those very special energy levels. And that explained both why atoms emitted and absorbed at particular frequencies, and it also explained why hot objects couldn't radiate infinite amounts of energy. Now, I should say, of course, there's Schrödinger and Heisenberg's. So what I've just described could be called the early quantum theory up till about the mid-20s, 1920s. But it was a hodgepodge of rules, a funny amalgam of classical ideas and just postulated ways of modifying them. But for example, that oscillators could only have discrete energies. But it was Heisenberg and Schrödinger working completely independently that discovered a complete theory that predicted those two features. They were quite independent. Schrödinger based his on something called the Schrödinger equation, which was a differential equation for calculating a function, a complex valued function of space and time, from which you could calculate the various transition probabilities for atoms to absorb and emit radiation. Using a completely different mathematical method, Heisenberg discovered an equivalent theory, but within a year or so of the discovery in 1926, they were shown to be identical theories, just with different mathematical formulations. So our full complete theory of quantum mechanics dates from about 1925, 1926, when Heisenberg and Schrödinger put it into a unified mathematical framework.
What is the collapse of the wave function?
Okay, so we now come to one of the curious aspects of quantum physics, and perhaps I can just ask or just explain what are the two key principles that underlie quantum physics, the two key facts that we discovered about the world that are very hard to understand. The first is that the world is a source of irreducible randomness and uncertainty. That is, no matter how far you carry the experiment, there will always be some things you can measure that remain uncertain. And this was in direct contradiction to the physics of Newton and Einstein, who regarded uncertainty as just a lack of knowledge. That is, by being more careful and carrying the analysis further, knowledge could be refined to such a point that uncertainty could be reduced to zero. But we know in quantum physics that's not true. In quantum physics, if you know everything there is to know about a way a physical system is prepared, so how an atom was prepared, its temperature, and so on, there are two things which hold simultaneously. One is there's at least one thing you can measure, the results of which are completely random. And simultaneously, for exactly the same state, there's at least one thing you can measure for which the results are certain. And it's this same way in which irreducible uncertainty and certainty coexist in a quantum description of the world that we find so hard to understand. So let me come now to the so-called measurement problem. When you are asked to explain how quantum mechanics makes predictions, you have to ask, how does it predict the probabilities of getting different measurement results? So it's one thing to say this an irreducible source of randomness, and sometimes you can make it certain. The real question is, what is the probability? How do you calculate the odds of a given measurement result? And it was up to Max Born to realize that the way you get it is to take a more fundamental object, which is the wave function, or more generally you could call it a probability amplitude. There's no good name for it, but it's not a real probability. In fact, it's not even a real number. It could be negative or it could be complex. But Max Born realized that you would get the probability if you took the square of that number, the absolute value squared. It's called the Born rule, and it enables you to make predictions about the statistics of measurement results. Of course, when you actually do an experiment in the lab, you get a result. You get one result, and if you repeat it, you may get the same result, or you may get a slightly different result. And as you repeat it, you gradually sample the probability distribution that Max Born predicted. So the puzzle in quantum physics is to, first of all, try and see if we can explain why in any given setting we get one particular measurement result. I think it's probably hopeless because of the fact that quantum mechanics indicates the world is irreducibly random. I know in the classical world we like to think that when you measure something, it tells you what that something was before the measurement. But in the quantum setting, it doesn't do that. In a very real sense, quantum objects don't reveal their objective properties when you observe them. They, in a sense, create objective properties under the act of observation. So it's probably better to start with measurements and say, we make measurements on the world, those measurement results fluctuate. How do I calculate the odds, the statistics of those fluctuations? Well, in some settings, we have to use quantum physics to do those calculations. But people have always worried, what happens next? If I measure, say, the position of a particle and find it at a certain point in space, what probability amplitude or what quantum state do I assign to the particle conditioned on that result? Same idea happens in classical physics. If I don't know whether I toss a coin, it could be head or tail, and I don't know which, I would say it's 50-50 until I look. And then, of course, it's definitely either a head or a tail. In a sense, the uncertainty collapses to certainty under the act of observation. Exactly the same thing happens in quantum physics. The slightly disturbing thing is that the probability is not primary. It's this quantum state, this thing that underlies it, which is primary. And so you have to change that state when you make an observation. To some extent, it's the strange coexistence of the Born rule, which enables you to calculate probabilities, and the quantum physics of Heisenberg and Schrödinger, which evolve states continuously in time. The Born rule, people have tried to derive it and come up with some deeper physical explanation of it, but no one has succeeded, I think, to this day. There are some pretty convincing statements you can make to motivate it, but no proof. And it's the difficulty in the measurement problem is to say, if I only have quantum mechanics of the kind that Heisenberg and Schrödinger derived, how can I get the Born rule? How can I predict that I need to take the mod squared of the wave function to get a probability? And why does that describe measurement results in the lab? And I think it's safe to say there's no convincing explanation of that. There are some things you need to take into account. One is that a measuring device has to be irreversible. It has to produce a result in some finite amount of time. So it has to be irreversible, and the device that's making the measurements has to have some space-time coordinates associated with it. It has to be somewhere and go off somewhen in order to record a result. And it's that curious way in which we just slap space-time coordinates on measuring devices from outside of quantum mechanics that leads to many of the puzzles of trying to understand what quantum mechanics is telling us about the world before we make those measurements.
How do we make the measurements, and what do we mean by observer? It seems to me that people are very confused when it comes to the term observer, me included, and then I think perhaps that also creates misinterpretations about philosophical frameworks of reality. I know a lot of pop science uses quantum mechanics to provide alternative explanations of what reality is, but I wonder how much of that is just confusion of what we mean by observer, what we mean by measurements, and if you could enlighten us.
Sure. To some extent, much of the confusion resolves itself into confusion about probabilities and what they mean, even in the everyday world. When I say you toss a fair coin but don't look at the results, the probability for it to come up heads is a half, and the probability for it to come up tails is a half. In a sense, I'm not measuring the probability when I toss the coin. What I'm measuring is whether it's heads or tails. And you construct the probability by doing many, many trials. So in some sense, probabilities aren't measured. They're sampled or estimated based on other kinds of observations. Now, because quantum mechanics only enables us to talk about probabilities, it's compelling to ask that those probabilities reflect ignorance of some fact of the matter that was the case before the observation was made. But that turns out to be wrong. It's not the case in quantum mechanics that probabilities reflect ignorance. They reflect something deeper, which is this probability amplitude. But because people are used to dealing with probabilities in the everyday world, and they intuitively know that while you can't measure probabilities, you can estimate them by trying the experiment many times. And when you do each experiment, you see some fact of the matter, a head or a tail. They like to carry that projection of reality back over into the case of measurements on quantum systems. So part of the confusion is just a confusion about probability and measurements in general. Now, of course, experimentalists are not confused about what a measurement is. They spend a lot of money to buy very particular kinds of apparatus if they want to measure something in the laboratory, whether it's a voltage on a resistor or a count of photoelectrons in some optics experiment. So there's never any doubt for the experimentalist what the measurement is. And of course, they're not worried about the fact that measurement results are not certain. They know before they begin that the measurement results will not be certain. Even in the classical case, they'll fluctuate from shot to shot. as I said before, what's puzzling is that uncertainty can't be reduced to zero in general because the world is quantum. So it's just a fact of the matter in the lab that you can make measurements, and there's never any confusion about it. I guess the question you might like to ask is, where and when is the measurement result recorded, I suppose? In the experiment, a measurement apparatus, as I said before, is a highly irreversible object. For example, if it's based on a switch going from on to off or off to on, once it switches, it stays switched. If you count 10 photons, it's a fact of the matter in the electronics of the device that there's a 10-photon pulse coursing through the electronics. So the measurement apparatuses are highly irreversible. They're also macroscopic, as I said. They're macroscopic in the sense that they have space and time coordinates associated with them. And perhaps we can come back to this a little bit later. In no sense can you associate space and time coordinates to unmeasured quantum objects. You can only assign space-time coordinates to the apparatus that records an event. And that's part of the reason why people have great trouble thinking about the picture of the world revealed by quantum mechanics. So let me give you a simple example. We often talk about the superposition of quantum states. So if I have a single photon heading towards a 50-50 beam splitter, a device which classically would reflect half the light and transmit half the light, but if I only have one photon going towards it, it has a probability of being transmitted of 50% and a probability of being reflected by 20%. And we sort of have in our heads this picture of a photon getting to the beam splitter and tossing a coin to decide whether it gets reflected or transmitted. But in fact, that's not what happens in the lab. You have a source of light which points it towards the beam splitter, and you have two detectors, one in the reflected path and one in the transmission path. And all you really know is that every time you press a button to send light in, one or the other of the detectors goes off, but not both. Your picture of a little particle whizzing down and making a random choice is just that. It's just a picture. The quantum theory, which tells you how to calculate these probabilities, doesn't refer to photons as little particles making random choices in the sense that a billiard ball might. It's not that at all. And this becomes particularly acute if you take away the detectors, one in the reflected beam and one in the transmitted beam, and just put mirrors there to send the particle back the other way again. What you will discover is that it's completely time reversing. If I don't detect whether it was reflected or transmitted, but just put mirrors there to send it back, it always goes back to the source with probability 1. So what was initially irreducible uncertainty, 50% reflected, 50% transmitted, if you don't look, you can return it to certainty. So clearly the picture that the photon actually makes a choice to be reflected or transmitted is wrong. It's only the correct way of describing it when you actually check to see if the choice has been made. If you don't check, if you make it impossible to check by putting mirrors in the reflected and transmitted path and just send it back where it came from, you can't say that the photon made a given choice at the beam splitter. So our classical intuition that particles have positions and velocities regardless of whether we look at them or not is failing us in the case of quantum measurements. So there are the two reasons for confusion on this subject.
So you explained measurement to us. I'm still confused when it comes to what we mean by observer.
Okay, so let's push on this concept of an observer. So you may be aware that with the rise of machine learning and artificial intelligence, there's a huge push to build so-called self-driving laboratories. These are fully automated laboratories that are stuffed full of equipment. They're connected to machine learning computers, but they're real things in the world. The computers turn on and off particular measurement devices, and they turn on and off access to measurement objects, different materials or gases or atoms. And everything runs in a completely automated fashion. What happens, of course, is that the experimentalists could be there and set it up and record the data on a piece of paper, but they don't need to be. They can completely automate it. So the measurement results take place. The records are stored in a computer. The AI looks at the measurement results, studies these statistics, figure out what's happening, and then adjusts the experiment for the next trial. And you ask yourself, where is the observer in that picture? There's no human there. The human may never need to be in the loop. You might want to put a large language model to enable humans to talk to it and for it to talk to the humans, but there's no absolute necessity to do that. It could just run in a completely automated fashion and build a new kind of molecule that might be better at harvesting light in photosynthetic systems. And you say, great, the computer did the experiments, learned what to do, constructed the molecule, and now I'm just going to build a product and sell it. Where's the observer in any of that? Well, you'd like to say that while there was no human observer in the loop, there was some sort of observation going on. And what was that observation? Well, it was, again, the irreversibility, an irreversible act of recording a classical number, a classical measurable result, a voltage or a count on a detector, or a magnetic field in some spin-based system. So there is some classical measurement record, a binary string of numbers corresponding to fluctuating voltages. And that is this irreversible act of measurement. Now, it doesn't matter whether a human looks at it or not. You could set up a completely automated procedure to take that data and learn something from it. But it's still the case that the measurement was itself irreversible, and the pieces of apparatus in the system all had space-time coordinates stuck to them. So they're the two defining characteristics of an observer. One, that it's an irreversible process, and two, it occupies some space and occurs over some duration of time. And perhaps we can get onto this, but the reason we give space-time coordinates to measurement devices is because they can fall in a gravitational field. And so there's a very deep connection between gravity and their ability to do measurements in the quantum world.
What do you mean by irreversible?
Yes, it's a good question, and it takes us back to the beginnings of thermodynamics in the 19th century, where it was seen that there are some processes that are easy to do in one direction but hard to undo. So, for example, if you had a container of hot water, it was easy to get a container of cold water just by waiting. It would just irreversibly cool. But if you had a container of cold water, it was not easy to get a container of hot water. You had to actually get some heat and some fire and do work on it and heat it up. And so there were some things that spontaneously ran in one direction, but couldn't spontaneously run in another direction. And it's generally a fact, perhaps the most fundamental fact of existence, is that things tend to decay and decline and die and fall apart. Irreversibility is written into the very core of experience. And to turn it around, like to make cold water hot, you have to intervene on the world with energy in order to change it. So irreversibility just refers to the natural tendency of some systems to change their state in time, to go from hot to cold, but it's very hard to go from cold to hot.
And the other thing you mentioned was we have to assign space and time coordinates in order to make an observation.
Yes.
So how do we do that?
Nobody really worries about it, because if an experimentalist doesn't know where their bits of apparatus are, they're in serious trouble. In the lab, it's just taken for granted that when they put a mirror on a certain part of the optical table, it stays there unless they move it somewhere else.
Yes.
There's no doubt about the matter that the world we work in and deal with always comes labeled with particular places and particular times at which things happen. So we never really examine it, and it's part of the problem in understanding the puzzles that arise in quantum mechanics. It's the core of what is difficult in understanding the violation of the Bell inequalities. Perhaps I could talk about that for a little bit. So one of the features of quantum physics connected with this irreducible uncertainty was made very clear by John Bell. And he said, let's discuss it in the case of photons, which is not precisely what he said, but the idea is the same. Photons can be polarized horizontal or vertical, or left circular or right circular. It's a sort of single binary property or choice that you can choose for the state of a photon. And there are certain processes which simultaneously produce two photons that travel in opposite directions and have opposite polarization. So you could have a little source that when you press a button, fires a photon to the left with horizontal polarization and a photon to the right with vertical polarization. How do I measure whether it's horizontal or vertical? Well, I just put a polarizer and keep rotating it till it goes through with certainty. And the orientation of the polarizer, where one photon goes through with certainty, tells you the direction, say horizontal. So what you discover if you have a source producing little pulses of light going in opposite directions with opposite polarization, in order to get them to be completely transmitted on either side, the two polarizers have to be at right angles to each other. One has to be horizontal and one is vertical. And you can just sit there and fiddle with it till you get that right. So now you know for sure that whenever I measure one horizontal, the other one will be vertical. And when I measure one vertical, the other one will be horizontal. And that's just a correlation, nothing particularly surprising about that. What John Bell realized is, what would the statistics be like if I rotated the polarizers by just a little bit? So instead of always making certain that the horizontal one went through with certainty and the vertical one went through with certainty, if I just made them a little bit less certain and get all these statistics and calculate correlation functions, he proved that the correlation functions that you would find in the experiment lie outside the class of any possibility of obtaining them with classical statistics. So the correlations that you see when you don't measure them in those particular directions are very surprising. It's as if there's some deeper level trying to bias the statistics of the measurements. So in classical physics, you'd say, well, the reason I see one horizontal for sure and one vertical for sure is, in fact, they are actually horizontal and vertical right at the start. And this is the error that we make in trying to prescribe properties to objects on the basis of a particular measurement of those objects. What John Bell showed is, if I don't make those kinds of measurements, make slightly different measurements, the statistics I get are inconsistent with assuming the photons have definite properties before I measure them. Now, for many people, it looked like the only way to explain what was going on is that somehow or other the choice of measurement I made on one particle influenced the outcome of the other one, that there was some kind of spooky action at a distance. And you can see that that can't be the case, because I don't have to do this experiment by putting the measuring devices on opposite sides. I could just take the measuring devices out and put mirrors there, reflect them back to the source and do the measurements there. It's not often discussed this way. It's a little bit hard to describe without a picture. But basically, instead of in the Bell experiment sending one particle to the left and one particle to the right, you still do that, but you put mirrors there, slightly asymmetrically located with respect to the source, and send them back to detectors at the source. You still do exactly the same measurements that Bell described, and you still get exactly the same funny correlation functions that you would have got in the other case, where the detectors were in the place of the mirrors. So now they're not space-like separated. The two detection events occur at the same place, but possibly at slightly different times. So you can't have it both ways. You can't say, well, the reason I explain these funny correlations when the detectors are at different positions is because of some spooky action at distance, when exactly the same phenomena is seen when the detectors are right on top of each other and just going click, click at different times. In other words, the space-time coordinates of the detectors in the Bell experiment are irrelevant to the explanation of the phenomenon. They're puzzling because we come in from the outside and put space-time coordinates on the detectors. But if I don't tell you what those are, it doesn't matter. The correlation functions do exactly what John Bell said they did. And so it's clear that the space-time coordinates of the detectors is something coming in from the outside of quantum physics. It's not intrinsic. And the Born rule doesn't assume any particular knowledge of the space-time detectors, where they are. It just wants to know what direction were the polarizers set at. So, to some extent, the space-time coordinates are just taken for granted, and they often mislead us in understanding what is the quantum phenomenon that's revealed. Now, in the setting where in the original Bell experiment, where the measuring devices with their rotating polarization directions were in different positions, you can ask, well, what does classical physics say about two measuring devices in different positions? In what sense do we know that they're in different positions? Well, we know from general relativity that the reason we regard them as being in different positions is there's a slightly different gravitational field at each detector. If we let each detector fall, they would fall on unique geodesics. If they were falling on the same geodesic, it's the same detector. There's a sense in which the very fact that we distinguish these two detectors at all is implicitly underwritten by general relativity. And now we come to the deepest issue of all. We have no way yet of reconciling general relativity with quantum physics. So if the space-time coordinates of detectors matter, and we know that those space-time coordinates are determined by the gravitational field, and we have no way of reconciling quantum physics and gravity, we have no way of answering some of these deep questions in measurement theory at this stage. But we will, I'm sure.
Okay, I have lots of questions. So perhaps let's start with a big picture one. What can quantum technologies do that other types of technologies can't?
Okay, so I said before that the quantum theory enables us to calculate these mathematical quantities called wave functions or probability amplitudes. And once we have those, we can calculate the statistics of measurement results. The astonishing thing about the quantum theory is it tells us how to very carefully change the probability amplitudes at the deepest level and change the odds that we see in measurements. We can deterministically change probability amplitudes by actually manipulating the world at the level of the quantum description. It's as if you can bias the outcome of measurement results by pushing your control levers deep down into the quantum realm and steering things around. So you can make complete certainty into complete uncertainty and back again, just like in the case of photons at beam splitters being reflected or transmitted. Now, initially, we discovered these rules just by going out and finding quantum stuff and studying it, just atoms and photons and all the rest of it. But once we understood the rules, we realized we could build machines that would enable us to control the probability amplitudes at will. And that's what quantum technology is. It's the ability to build machines that we can control at the deepest level of control, which is at the level of the quantum state or the quantum wave function, and deterministically drive things towards particular outcomes. Even though the measurements will always be statistical, we can change the distributions. We can bias the odds, if you like, at will. And that's not something that you can do in the ordinary, everyday classical world. And even more importantly, the sorts of correlations you can generate by intervening in the quantum world are completely different from those you could get if the world was classical. And it's those strange correlations that enables us to do all the astonishing things that we can do, such as quantum computing or quantum sensors. So in summary, quantum technology is the ability to control the world at the level of quantum states.
How do you bias the odds?
Okay, so here's a nice example. Let's suppose you want to go back. So let me go back to the photon experiment. I said if I send a single photon into a beam splitter, 50% of the time it's reflected and 50% of the time it's transmitted. Now ask yourself what would happen if I put two identical photons in from opposite sides. So one is coming down towards the beam splitter and one is coming up towards the beam splitter. If each is making a 50-50 choice, you would think that there's 1/4 of the time both will be reflected, 1/4 of the time both will be transmitted, 1/4 of the time it'll be transmission reflection, and 1/4 of the time will be transmission reflection. So if it's a coin toss for each one, the 4 possible outcomes, reflection, reflection, transmission, 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 reflection, reflection, transmission, should be equally likely. When you do the experiment, you discover that you never, ever get a result that you could say was due to the fact that both photons were reflected or both photons were transmitted. Because you never get the result where you get a single click on either reflection beam or transmission beam. What always happens is the photons bunch. After the interaction with the beam splitter, they both go in the reflected beam or both go in the transmitted beam down towards the other detector. So there, just by adding one other photon to a machine which was ostensibly completely random, you've completely changed the statistics of the measurement result. And it's as if you tossed 2 coins and said, I can get head, tail, tail, head, 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 tail, tail. But because I've tossed 2 coins in just the right way, I never get head, head, or tail, tail. That always completely disappears from the result. So that's an example of how we can change the observed statistics by the basis of manipulating matter and light, this case photons at beam splitters, purely by the quantum rules.
Interesting. And so with quantum computing, the speed of doing something increases.
Okay, so it's not so much the speed, it's the efficiency. So let me just explain that in a little bit more detail. First of all, let's talk about classical physics. Classical computing. The way you think of classical computing is you have an algorithm, which is a set of rules for manipulating numbers. And often the algorithm is designed for some particular hardware. And for over 60 or 70 years now, we've had algorithms based on binary numbers, changing strings of ones and zeros into strings of ones and zeros in as deterministic way as possible. The hardware we run it on is these massive arrays of switches, which are either 1 or 0. They're highly irreversible devices. Once it's switched from 1 to 0, it stays 0 until we turn it off again. Until we turn it back on again. And a classical computer can be thought of as a massive array of cascaded switches synchronized by some clock running in the background. So they're like falling dominoes, but in a complicated way, which dominoes fall when depends on where you start the whole chain off. So a classical computer takes binary strings at the input, clocks them through this device, and produces binary numbers at the output. And it's based on these irreversible switches that are in transistors. At least that's how we do algorithms today. It wasn't how we've always done them. In the 19th century, we used a completely different approach based on integers called adding machines, based on wheels, cog wheels, and so on. But these days we do it with binary numbers because it's easy to represent a binary number as a switch, which is on or off. And it was Claude Shannon in his master's thesis, I think at MIT around 1937, that sent us down this path of thinking of computation as turning things on and off with binary switches. So any number can be represented as a sufficiently long string of ones and zeros. And so a quantum computer also takes strings of ones and zeros and transforms them into strings of ones and zeros. But going back to the classical case, you may ask yourself, how many clock cycles, how many steps do I need to run the classical computer for to transform one binary string into the desired binary output number? In other words, how many steps does the computation take to do the calculation? And more particularly, how does the number of steps change with the size of the number going in? Efficient calculations can be done with not many steps, and the number of steps doesn't change very much whether I do it on 100 binary strings or 1,000,000 binary strings. But there are many computations which are highly inefficient, and the number of steps you need to execute increases exponentially with the number of binary numbers that you input to the problem. They're called inefficient. And you may ask yourself, well, is that due to the algorithm or is that due to the hardware? But you can't really separate the two because, as I tried to explain, the algorithm that you choose to transform ones and zeros into ones and zeros is designed to run on a particular kind of computer built out of switches. But what we discovered in quantum computing is, while it's still true, you have binary numbers in and binary numbers out, it turns out the number of steps required for certain problems doesn't scale exponentially with the size of the input bits. That you can transform strings of binary numbers into the desired output strings of binary numbers far more efficiently if the hardware is quantum and not classical. If what's in the box is not a bunch of silicon switches turning on and off, but something quite different, some quantum materials, some quantum devices, something that you control at the level of probability amplitudes. If that's what's in the box, there are certain algorithms that enable me to transform one binary string into another binary string with exponentially fewer steps than I would have had to have used on a conventional computer. So the real question is, what's in the box?
Yeah, that's my next question.
What's in the box?
Yes.
So we would like to say that there are physical things rattling around in the box, colliding with each other. Their states are changing with every collision, and they follow various paths, and they come out the other end, and we detect them as ones and zeros. We'd like to say that. But I said at the very beginning, if you don't look, if there's no way of knowing what happens between input and output, you can't ascribe definite trajectories to particles as if they were classical billiard balls. And so that picture fails immediately. So what you have to do is make sure what's in the box is something that doesn't, even in a hidden way, carry information about which switch is turned on and which switch is turned off. It must always be the case that the switches in the box are left in a superposition of 0 and 1, that no attempt is made to determine what they are. Only at the output do you make a measurement to see which ones are on and which ones are off. So that's the key, and it's the probability amplitudes that you're controlling with outside voltages that ensure you can still change what's happening inside the box, even without knowing what's inside the box. You can apply a voltage and change the plane of polarization of a photon. You can apply a magnetic field and change the direction of some spin of some particle. As long as you don't measure it and check what it is, you can continue to work with the probability amplitudes. There's another way in which I think it might be helpful to understand what's happening in a quantum computer, which maybe now that people are becoming more familiar with machine learning could have a bit of traction. So the standard way we think about computation is deterministic. If I want to calculate the value of some function, say the addition of 100 numbers, it's completely deterministic. I either get the right answer or I don't. There's no doubt about it. But there are many calculations that are not like that really all you care about is just doing random samples to get the result. But we tend not to think about that very much in in standard computing until the rise of machine learning. In machine learning, essentially what you're trying to do is find a way to program a machine to calculate an unknown function, which seems hopeless. But when I say unknown, the function may be unknown, but you do have some examples of some inputs and some outputs. And in machine learning, what you're going to try and do is build a device that, at least on the examples you know, gets the calculation right most of the time, not always, but most of the time. That is essentially what a machine learning algorithm is. And now you can use it on inputs that you don't know the answer to, and you hope that most of the time it's still right. So there's a deep way of thinking about machine learning, and that is transforms one set of probability distributions over binary numbers into a different set of probability distribution over binary numbers, where now the new distribution over binary numbers encodes this function that you've tried to learn. So if the function says, I put in 2 bits and the output is only 1 if the bits are the same and 0 otherwise, I can set up a little machine learning algorithm to do that. It means if I put in a uniformly distributed set of 1, 0, 0, 1, 0, 0, 1, 1, what will come out will be just 2 possibilities, 1, 1 or 0, 0. So thinking of computing in terms of machine learning as transforming probability distributions on binary numbers carries over immediately to what happens in a quantum computer. Because in a quantum computer, in a very real sense, is dealing with irreducible quantum uncertainty right from the get-go. And it's always classical bits in, classical bits out. It just so happens that if what's in between is quantum mechanical, I can generate a vastly greater variety of probability distributions at the output than I could ever have done with a classical computer. And it's that incredible richness of probability distribution over binary numbers that is achievable with quantum devices that gives me new power to do computation with quantum hardware as opposed to classical hardware.
What's the new things that we can create as a species now with this new technology?
Right. So I wrote my first paper on quantum computing in 1988. It was a very long time ago, and it was to do with photons at beam splitters, building a so-called Fredkin gate. And in those days, quantum computing was very much a niche, if not slightly crazy field to be involved in. Hardly anybody was working on it. But people were working on it, were doing profound work as it later transpired. But in the early 90s, Peter Shaw, a mathematician or computer scientist, came up with an algorithm that would make no sense on a conventional silicon computer. But if you had a quantum computer, you could run it and find the prime factors of very large integers much more efficiently than you could do it on a conventional computer. You could do it on a conventional computer, but if the integer you were trying to factor had 500 digits in it, it would take the age of the universe to figure out what the prime factors were. You just have to keep trying every one till you actually get it. But he showed that if you had some quantum hardware, if you could build these quantum switches that I was describing before, which are neither 0 nor 1, that you can cleverly manipulate the probability amplitudes without ever checking at any point. If you could build those devices, you could find the prime factors of large integers very efficiently. And you might think, well, that's a pretty obscure result in number theory, but as I suspect most people now realize, the codes for public key encryption that we use on the internet to encode private data such as credit card numbers for public transmission is based on the difficulty of finding the prime factors of large integers. It's very easy to take 2 large integers and multiply them together, but it's very hard to go the other way. And that kind of one-way functionality is the key to encryption. But if a quantum computer, when we realized this in the early 90s, that if a quantum computer could be built in, say, 50 years, then all the secrets that are currently encrypted with public key cryptography would be breakable, they'd be open. And so a lot of money went into the field to see, is this feasible? Does it make sense to think that anybody could build a technology that could find the prime factors of large integers? And this led to the growth of quantum computing. Now, I don't know, 30 odd years later, from Peter Shaw, we know exactly what's required to build a machine like that. It's not going to be easy. We're a long way from doing it just now. You have to be able to not only keep everything quantum inside the machine and unknown until the output, but you have to make sure that sort of ordinary everyday levels of randomness, such as a cosmic ray or a bit of hot material, doesn't upset the computation. In other words, You have to be able to control the probability amplitudes yourself as efficiently as possible. There can't be anything left open to chance. If there is something left open to chance, we know we can fix it using something called quantum error correction. And this would enable us to build fault-tolerant quantum computers that will eventually be able to implement Shor's algorithm. It's probably some way off. I'm not entirely sure how long, maybe 5 years, maybe 10 years. So that was the big ticket item, if you like, the extreme sports version of quantum algorithms. But in the intervening time, we know that there's lots and lots of other interesting things we could do with a quantum computer. In fact, Feynman originally suggested the best thing you could do with a quantum computer is simulate quantum physics. Because quantum physics is unexpectedly difficult to do on a classical computer, requires knowing all these probability amplitudes, he suggested, well, just build a quantum device to do the computing. And so there's lots of things that we'd like to be able to run quantum computers on. For example, designing new drugs by using quantum chemistry simulations of how the various constituents combine, how various functional rings and functional backbone of proteins combine, design it all very carefully using a quantum computer to model what things you need to put into the mix. Designing new materials. For example, we know that superconductivity relies on very subtle quantum features that just happen to occur in certain metals at low temperature. It'd be really nice if we could figure out new materials for which those nice things happened at high temperatures. And so many of the hot applications of quantum computing are about modeling the world and predicting new materials and new ways of doing chemistry for drug design and so on. That would be done much more efficiently on a quantum computer than a classical computer. But we've also discovered some other curious things along the way. For example, in our work at NQCC, not me personally, but we're using simple quantum algorithms to get far more efficient fraud detection in financial data. That is, most of the time, the data that's rattling through some banking network is perfectly legitimate, but every now and then, with some very small probability, there's a fraudulent transaction. You'd like to be able to catch that in real time and flag it. And it just so happens that the unusual statistics that quantum physics, quantum states, quantum computers can produce is very good at finding anomalies like that. Similar sorts of things happen in particle physics, where you want to find very rare events and characterize them on the basis of experimental results. Again, it looks like there are good quantum algorithms that will run on relatively simple quantum hardware that will enable you to do that very efficiently. So from the sort of extreme sports end of factoring large integers to modeling new materials, quantum computers will be useful. But I think there's another way in which they'll be useful as well, and that is as an interface between classical machine learning and the quantum world. So one way to think of a quantum computer is it's a kind of quantum controller for matter. It enables you to take ordinary everyday classical signals and control matter in a very exquisite way. So in these automated laboratories I was talking about earlier, you could imagine putting a quantum computer between the classical machine learning and the actual stuff that you're trying to test or evaluate or control, so that the quantum controller or the quantum computer would be sending out single photon states, and single photon states would be coming back, or sending out, qubits and getting qubits back, making the measurements and producing these very unusual statistics that then is passed off to a classical machine learning algorithm for the next step. So I believe that one of the most important applications of quantum computing will be as an essential interface to provide quantum data to classical machine learning protocols.
Interesting. This makes sense. So in order for me to understand more, with classical computing, the hardware has binary silicon switches.
Yep.
But with quantum computing, do we still have switches?
You still have devices which, when you measure them, are either 1 or 0. But when you don't measure them, there are infinitely many possible states. It's just determined by a probability amplitude for it to be 1 or 0. So I can control the probability amplitude to make the measurement to be 1 with certainty, or I can control the probability measurement, the probability amplitude to make measurement 1 50% of the time, 0 50% of the time, and all the way through to control the probability amplitude to make 0 certain. But the trick in a quantum computer is to have all that capability at the individual switches, but never actually look at the answer till the very end, after you've done a cascade through possibly millions of such quantum switches. So you never actually know inside the machine which quantum switch is off and which quantum switch is on. All you know is at the end, certain quantum switches are on and certain quantum switches are off.
And what material is this?
There are many different ways of building it. So one of the early ideas was trapped ion quantum computing. So you can think of a trapped ion quantum computer like this. You have some atoms that you're going to bang together. But inside the atom are electronic states which are fully governed by the rules of quantum mechanics. So let's to keep it simple, let's just say inside each atom there are two quantum states. Could be 0, or it could be 1, or it could be some amplitude superposition of both. So inside the atom is a little quantum switch, if you like, which is only 1 or 0 when you look at it. So what you can do in an ion-trapped quantum computer is you can take two atoms that have this little switch inside, bring them close together so they collide, and then move apart again, such that when they collide, the internal states of the atoms change in a conditional way. It may, for example, be the case that if the internal state's about 0, nothing happens to those states when they collide. But if the two internal states are 1, 0 and 0, 1, when they separate, you can't be sure what the state of the two atoms is. It could be like a quantum coin toss, where it's some superposition over all possibilities. So you can think of quantum switches as like that. You have some external degree of freedom, like the motion of the atoms you can control. You bang them together and you bring them apart. But it's during that interaction that quantum dynamics begins to change the internal states of the atom, which is where the information is hidden. And later we discovered that you could do this with neutral atoms as well. You could trap neutral atoms in so-called optical potentials and just move them around and let them collide with each other. And then once you've separated them, you can start using lasers to read out what the internal states are. So ion traps control collisions, neutral atoms control collisions is one way to do it. Another way to do it is with quantum circuits. So last year the Nobel Prize went to Clark Deveray and John Martinez for work on demonstrating that the quantum rules apply to electric circuits. It's sometimes thought that quantum mechanics only applies to atoms and atomic-sized things, but in actual fact, the theory doesn't say that. The theory says it will apply to everything if you're careful enough. It's really just a question of engineering. And so what these people realized was that I could make circuits which are governed by, V equals IR and, Ohm's law and all these sorts of things, behave in an entirely quantum mechanical way if they were superconducting. So that the things like voltages and currents and charges would be subject to the quantum rules, not the classical rules. And many years later, in the early 2000s, a number of people realized it was possible to build circuits that would literally be quantum switches that were superpositions of ones and zeros. So these superconducting circuits are quite complex arrangements of wires on silicon or sapphire substrates. They look just like ordinary old printed circuits, but if you cool them down, they become superconducting and all the rules change. They now are governed entirely by quantum rules, and so you can build quantum computers out of these devices. By cool them down, they have to be pretty cold. They have to go into dilution fridges at sort of tens to hundreds of millikelvin, not a trivial matter. But the technology is progressing astonishingly fast. And both IBM and Google and Rigetti have machines you can buy to do superconducting quantum computing. The National Quantum Computing Center that I work for is currently running a competition to devise novel algorithms that will be run on the Google's Willow superconducting quantum computer chip. Sometime in the next week or so, we'll we'll have a look and see what we've got for that competition. I imagine there's some pretty exciting stuff there. But those devices just look like bits of wire on a surface, like a printed circuit. But when you cool them down to millikelvin temperatures, they behave like quantum physics as they should. So that's trapped ions, trapped atoms, superconducting. Another one that I'm pretty keen on is based on photonics. So most people know that the backbone of the internet is optical fibers. There are little pulses of light coursing down those fibers.
I don't think most people know.
Most people don't know that? Okay, well, I thought at some point various internet service providers were boasting about fiber to the house.
I see.
So that must be a very mysterious statement if you don't know that it's optical fibers, not copper cable that's carrying your signal. But anyway, it's just a fact of the matter that the incredible bandwidth of the internet, our ability to stream video, is due entirely to the fact that it's mostly optical fibers that are carrying the signal through little pulses of light. Because, these optical pulses can have such a high frequency, optical frequencies, the bandwidth is enormous. Now, that technology does a lot of amazing things with pulses of light, but all those pulses of light are classical pulses of light that come out of lasers. And you have to be able to make fibers that'll switch a pulse from one fiber to another depending on whether there's a control pulse present. And so there's a huge technology built up in controlling how fibers switch purely by light. And so you think to yourself, I have a way to switch things on the basis of light. It behaves classically at the moment, and the optical companies have got incredibly good at building very fast switches. Sometimes they have to bring it back up to electronics and then take it back down to light. But you ask yourself, well, if I could run all that with quantum states of light, with single photons instead of laser pulses, could I build a quantum computer that ran just like the way we process optical pulses in the internet? And it comes back to what we discussed at the beginning. Photons at beam splitters behave very strangely if they're truly photons and not just classical electric and magnetic fields. And many years ago, back in 2001, working with Manny Nil and Ray LaFlamme, we figured out a way that you could do universal quantum computing with pulses of light, so long as they were photonic, the true single photon states. You had to do some tricks connected with measure and feedback. You had to check every now and then to see whether the photon is where it should be and then change the network on the basis of that. Subsequently, Michael Nielsen, who was working with me in Brisbane at the time, came up with a better way of doing it that didn't require so many resources in terms of fibers and beam splitters. But the real breakthrough came when Terry Rudolph and Dan Brown in London in about 2005 realized that there was a far better way of doing it if you could use the natural ability to produce photons of the kind that are produced in the Bell experiment, that are highly correlated. If you could at least produce pairs of those things, you could make use of this optical protocol to do very efficient quantum computing with light. And that led to something called fusion gates, which led to the founding of a company called PsiQuantum by Terry Rudolph and Jeremy O'Brien. Jeremy O'Brien was at the University of Bristol at the time. They subsequently moved to Silicon Valley to get funding to do it, and they founded a company called PsiQuantum, which is now building quantum computers in Palo Alto in Silicon Valley, in Chicago, and in Brisbane in Australia. The hope is to build quantum computers just right from the get-go, have hundreds of thousands to millions of quantum switches encoded as pulses of light in the device. There are other ways of doing it with light. Xanadu is a startup company in Canada, in Toronto, that does it slightly differently with pulses of light. And the verdict is out on which of all these different ways will ultimately give us something powerful enough to do universal quantum computing, fault-tolerant quantum computing. So I wouldn't like to say which one's going to win. It'll be difficult, no doubt about that. But now, I have a feeling no matter what happens, photonic quantum computing will be in the mix, because we need to be able to move quantum information from one local quantum computer to another, if only to check and verify that it is behaving quantumly and not being spoofed in some way. Optics will always be part of the mix.
So this is part of quantum optics.
The photonic quantum computer is quantum optics, indeed.
Explain us quantum optics from very big picture. What is quantum optics, and we'll go deeper into the rabbit hole as we go.
Okay. So once Maxwell realized that light was just electromagnetic radiation and self-sustained oscillations of oscillating electric and magnetic fields, people realized there was a way of explaining the wave phenomenon that optics tended to exhibit, such as interference of light, which goes back to the 18th century. Light, as conceived by Maxwell and as experiments demonstrated, was just like waves. And all of classical optics is based on the assumption that light behaves like waves. It's refracted as it passes between an interface between two media with different refractive index. It diffracts around edges. It undergoes interference when crests meet troughs. And all of physical optics is based on our understanding that light is a wave, and it's based on the theory of Maxwell. However, we knew from the early part of the 20th century, with Einstein's explanation of the photoelectric effect, that there are some experiments which requires you to think of light as if it were a rain of particles, where the energy of each particle was determined by the color of the light, and the number of particles per second was determined by the intensity. So this is completely different from the Maxwell picture of waves, light being waves. Now, it took 30 or so years after Einstein, perhaps more, for people to realize that there is a consistent quantum theory of light. It's called quantum electrodynamics, and it was well and truly established by the mid-50s. It was often only applied in the most extreme situations where relativistic effects were important, where you had incredibly high energies, such as positrons and electrons annihilating each other, or electrons or photons scattering, high energy gamma ray photons scattering off matter. But quantum electrodynamics applies to all electromagnetic phenomenon at any frequency and any energy. And applying the theory of quantum electrodynamics to slow-moving electrons, such as the ones you find in atoms, and optical frequencies of light, leads to quantum optics. That's what quantum optics is. It's the application of the quantum theory of light, which is quantum electrodynamics, to situations where we'd like to describe things in terms of ordinary wave optics. Now you might ask, well, if wave optics was doing fine, who needs quantum optics? Well, it turns out wave optics wasn't doing fine. There were many experiments in the 50s and 60s and 70s which couldn't be explained by ordinary everyday wave theory of light. You needed quantum electrodynamics, and it was Roy Glauber at Harvard in the 60s who realized how to apply quantum electrodynamics for quantum states of light. One of the earliest successes was understanding how lasers work, where you needed to understand how photons are produced by excited atoms inside an optical cavity. Later, you can try to understand how the statistics of photodetection changed as you change the source of light. We needed quantum optics for that. And finally, to understand these beautiful experiments, such as the one I described, where if I have two identical photons entering from opposite sides of a beam splitter, you never get a case where they're both reflected or both transmitted. They tend to bunch. They all go in one direction or the other. Something called the Honu and Mandel effect is uniquely quantum prediction of quantum optics. It doesn't happen for classical electromagnetic theory of light. So we need quantum optics for a great number of experiments, and more have come along in the intervening time. There's no accident that some of the best tests of the strangeness of quantum mechanics are done with quantum optics. Alana Spey, for example, got the Nobel Prize for demonstrating violation of the Bell inequalities with photons, polarization of photons. And the reason it's easier to do it with light is that at room temperature, there are very few random thermal photons floating around. If you have your photons at optical frequencies, the experiment is essentially at zero temperature. You don't see any random photons messing things up. So there's some examples. That's a sort of potted history of quantum optics. So in a nutshell, it's the quantum theory of light, valid outside of highly relativistic experiments.
I see. What are you currently working on?
At the moment, I might divide my work into two areas, basically. Firstly, I'm very interested in building quantum machines that learn. One of the things I believe is that by building quantum switches, we'll pay less of an energy cost for machine learning than we would if we were to do it as we're currently doing it with silicon devices. But even more so, once you realize that machine learning is about transforming probability distributions, and quantum mechanics gives you some very unusual probability distributions, it doesn't take an enormous leap of the imagination that quantum probability transformations might provide a very efficient path to machine learning. So I'm doing a lot of work on that, particularly in optics here at the University of Sussex. I have a PhD student, Josh Burns, and we're working on designing photonic, what are called photonic state space models for learning. You could think of them as convolutional networks, but instead of using pulses of light from a laser, we're using single photons that we would use in a quantum computer, but now for learning applications. So that's some work that's underway. But the other thing I'm keen to understand, and I have been working on for some time, is how to reconcile quantum physics and gravity. This has always been a passion for me, and just about every other theoretical physicist has thought about it for more than 10 seconds. We're now at the stage where we can control states of matter and states of light, that we can begin to think about how gravity might change quantum effects. So if I have a superposition of a particle in two different places, what is the gravitational field of that particle? Is that a sensible question even to ask? More particularly, coming back to my discussion of the measurement problem, where I try to suggest that it's the space-time coordinates of the apparatus that matter most, and that implicitly makes an assumption about gravitational fields. Is there a path there to understand what new experiments we could devise that would give us a hint on how gravity and quantum physics should be put together? I should preface this by saying that people have been trying to reconcile quantum physics and gravity since Einstein, shortly after Einstein invented general relativity, which is our modern theory of gravity. No one has succeeded in explaining any experimental or observational data yet. There are some beautiful theories which may yet turn out to be heading in the right direction. One is loop quantum gravity, associated with many different people, but Carlo Rovelli particularly.
I've read his book Order and Time.
Yes.
I definitely got very confused.
It's a beautiful book. Yes. He writes in a very sort of poetic style, which is inspiring, but perhaps to understand it requires a little bit more technical language. So and the other one is string theory, of course, which is what happens if you push quantum field theory to the extreme where you'd like to explain gravity. But so far, neither of these, I mean, they both feel perfectly consistent mathematical theories, but there's a lack of any experimental evidence as to which way we should jump, or observational evidence for that matter. One of the big puzzles and probably big hints as to something that's going on is the cosmological constant problem. As we know, the universe is expanding, but the expansion is accelerating. It looks like there's some sort of anti-gravity stuff pushing it apart on a cosmological scale. It's consistent with Einstein's theory of general relativity if you put a term called a cosmological constant into his equation. So you say, well, where does that come from? Well, if you say, well, maybe it's due to quantum fields, maybe it's just due to the vacuum quantum field that's floating around out there all the time from all these sort of ground states of various fields, electromagnetism, strong nuclear force, and so on. Say, okay, maybe it's due to the vacuum energy. You work out what the cosmological constant should be, and you find that you're out by a factor of about 10 to the 120 or something, some absolutely phenomenally bad prediction. So there's this question of what is this thing we're seeing that we interpret as cosmological constant? Does it have a quantum origin or not? And if so, what does it tell us about a quantum theory of gravity? I have some ideas on that. I'm working with my PhD student, Francisco Pippa, on this, and a student at Oxford, Pranav. We have some ideas. I've been involved in the theory of various experiments to test this with Sagata Bose at University College in London, where some years ago he and I and many others come up with an experiment to definitively tell us whether or not gravity should be quantized at all. Maybe gravity's not the sort of thing you quantize. It might be like the equation of state for an ideal gas, PV equals NKT. I mean, it's correct and it describes the physics, but you don't start out by trying to quantize it. If you want a quantum theory of gases, you do something completely different. Gravity might be like that. That would be puzzling because the way Einstein formulated it can be reformulated as a regular old Hamiltonian field theory, which we've been able to quantize in the past quite successfully, but so far failed with gravity, except in a very approximate so-called linearized sense. So this is something that occupies me more and more, is this question of reconciling quantum physics and gravity.
Okay. So, you mentioned we have a quantum loop gravity.
Yep.
You mentioned string theory.
Yep.
So, tell me if I understood correctly, we have certain, well, we have the development of quantum physics in this 20th century that suddenly makes us question our initial understanding of what gravity is, and thus we're trying to come up with a better theory that explains gravity, that makes it work within quantum physics.
Yes.
And these are, so can you explain us a little bit, and then I want to go a little bit into quantum Turing machines too, as you're working on them. Before we get into that, what are some of the differences, and explain us a little bit the different predominant theories now that are being developed to explain gravity?
Okay. So one idea, due to Roger Penrose and Las Diossi, is that whenever you try to make a strange gravitational field by taking a source, like a chunk of matter, and putting it in a superposition of two different places, say, the minute you try to do that, gravity will guarantee it will collapse into being on the left or the right, but gravity will really, in essence, measure where the particle is and localize it. It's called, well, it has various names, but Roger Penrose calculated a rate at which it should happen, which is determined by the self-energy associated with the distribution at the superposition. There's something really strange, and his intuition behind this is that when you have a lump of matter, the gravity, if it's just, actually it's a little bit difficult to talk of a lump of matter alone in the universe. That makes no sense from a gravitational point of view. So let's suppose a lump of matter in a laboratory. And so I have a reference frame where I know where it is in relation to everything else. In other words, I know where it is in relation to a background gravitational field. So for sure, if I let go, it'll fall in a gravitational field and it will move on a geodesic. And that geodesic is unique. Its entire past and future is fixed by the gravitational field of the universe. But if it's in a superposition, the geodesic is not unique anymore, so it's clearly inconsistent with general relativity. Another way to state it is the gravitational field of that mass is not stationary. It would look as if it was fluctuating between being on the left-hand side of the laboratory or being on the right-hand side of the laboratory. And that's a very strange notion, that the gravitational field should be noisy and stochastic at that level. But just the mere fact that the notion, in fact, you can cash it out this way. As I said earlier, quantum states the position and trajectories of particles, in a sense, don't exist unless you measure them. If I have an interference experiment between source and detector, if I don't put any detectors in between, in a sense, particles take all trajectories. That's what Feynman described it. But we know in each trial, you have one particle at the source and you get one particle at the detector. There was only one particle in the system, clearly. At least that's what you'd like to claim, given you only detected one particle. But to give a trajectory to it between source and detector is going too far. But that's clearly inconsistent with general relativity, which says that between source and detector, that particle was on some sort of geodesic, at least until it interacted with the source and detector. And so there's no way to assign a unique geodesic to a superposition of paths. And so this is part of the problem, that there's no consistent way to combine our description of the quantum world outside of classical trajectories in terms of the world of general relativity, where objects move on geodesics unless they interact with non-gravitational forces. There's another problem with time in quantum gravity. So actually, this is a subject that I'm also working on and have done for some time, trying to understand how you build really good clocks, because much of our technology relies on building incredibly good clocks. And in general relativity, if everything is quantized, when something happens is just as vague a notion as where something happens. It only happens in detectors when measurements take place. So it's well understood that trying to understand how time would arise in a quantum theory of gravity is very, very difficult. So these are some of the questions that have been around for decades in understanding the problem in quantum gravity. But if you really wanted to see the difficulty in a nutshell, you could ask, what happens to gravitational collapse if the collapsing matter enters a Bose-Einstein condensate? So a Bose-Einstein condensate, just put gravity aside for the moment, we've been building these things, making condensates since the 90s. Basically what happens is you take a bunch of atoms that are all colliding with each other and they're in some thermal distribution, and you start cooling them down so their energy goes down, their position uncertainty begins to be dominated by quantum effects until you get to the point where the relative separation between them is smaller than the position uncertainty of each atom. And now you can't really distinguish one atom from another. In a sense, they're indistinguishable. And now this funny feature of bosons to bunch, like two photons going into a beam split that tend to come out on both together on one side rather than the other. In the case of atoms, once it enters this quantum domain, once they collide, they all tend to end up in the same post-collision state, which is this condensate state. The condensate is like a coherent blob of matter. The notion that it's made of atoms is no longer a good picture, because you can't think of the atoms as having trajectories anymore. They've lost that as they've become part of this quantum state. So just keep that in mind. We have this condensed state of matter. We can make it and observe it, and it's incredibly useful. We're using it for all sorts of new quantum technologies, but it requires the atoms to be indistinguishable. They can't have any individual path. If you go in and measure where one is, it's no longer in the condensate. It gets kicked out. Now, let's look at what happens in the case of a simple black hole forming from collapse of dust particles. As the dust particles fall on geodesics, they could start interacting with each other through non-gravitational forces. You could imagine a situation where they could form some sort of condensate eventually. But now we have a deep puzzle, because if they form a condensate, each atom no longer can be associated with a geodesic, because it, in a sense, doesn't have an identity. And we know that the singularity theorems of Penrose and Hawking tell us that under those conditions, classical particles will collapse into a black hole behind an event horizon and form a singularity.
Explain us the singularity.
Okay, so I'm not an expert on general relativity, but the basic idea is this, that as classical dust particles, forget about Bose-Einstein condensating for the moment, but as classical particles begin to collapse under gravitational interactions, they eventually reach a point where their gravitational field is so strong that they can never escape getting to higher and higher and higher densities. The gravitational field keeps getting bigger and bigger and bigger, and that's reflected in the spatial curvature getting bigger and bigger and bigger. You won't see them because they'll be behind an event horizon, because eventually the gravitational field will be so big that light won't be able to escape. But according to the theory, the geodesics of all these particles ends in a singularity where the gravitational field is infinite, the curvature is infinite, the energy density is infinite, all these crazy things happen. And so, of course, no one believes that physically that nothing in physics goes to infinity quite like that. So something else has to happen at that point. But anyway, if it was all just collapsing dust particles, that's what general relativity would tell us. The hope is that it's behind an event horizon, so we can't see it, but it's no guarantee that that will always be the case. But now what happens if it forms a condensate before it enters the event horizon? What are there stars out there that are bosonic condensates with a strong gravitational field? The people have been suggesting this for some time as perhaps explaining dark matter this way. But there's something fundamentally inconsistent about a Bose-Einstein condensate and particles undergoing gravitational collapse. Now, there are some theories of exotic matter that shows that if matter is of just the right kind, so the mass gradually dissipates or fades away, it will avoid a singularity, it will collapse behind the event horizon, but won't become singular. Maybe quantum states of matter under gravitational collapse will be of that kind and avoid singularities. But if that's true, it says that somehow or other quantum coherence breaks gravity at some key point. Rather than gravity breaking quantum coherence, it's quantum coherence which breaks gravity, and that is deeply disturbing.
I see. Let's talk about quantum learning machines.
Okay.
I think, again, explain us how they differ from other types of machines that are classical.
Classical machine learning.
And also, I was going through your papers, just briefly, mostly I don't understand, but also I came across the standard qubit model, and
Oh, sure. Okay.
and
Yes, I think I know what you've. Okay, so the way we'd like. So let's back up a bit to classical computers, where once Claude Shannon set us down this path of computers as binary logic, things being on or off, and every computation was based on cascaded arrays of switches. We had a kind of universal abstract way of thinking about classical computation as different ways of combining fundamental combinations of switches like NOT gates and AND gates, and just more and more complicated circuits of those things could do any classical computation that you want, sometimes less efficiently, sometimes more efficiently, and a lot of effort went into finding the simplest circuits of Boolean gates that would enable a particular algorithm. And so that's the classical abstraction that all modern computing is based on: Boolean circuits, combinations of Boolean elements into Boolean circuits. So in the early days of quantum computing, people adopted a very similar abstraction. They wanted a way, let's just confine ourselves to quantum computation over binary numbers, so qubits, where when you measure it, you either get 0 or 1. They needed a way to universally generate all the possible probability distributions you could get over, say, n qubits. And they didn't want to have to, model every particular bit of quantum stuff in detail in order to do that. So they adopted a very similar approach to what's done with classical switches. They said, let's start with an elementary quantum switch, which when you measure it is either 0 or 1, and an elementary two-state quantum switch, like a collision between two quantum switches, which enables you to generate a particular kind of joint state of the two qubits. Now, it's important to realize that that picture is to some extent very an uncomfortable mix with quantum physics, because quantum physics, the probability amplitudes are continuous functions of time and continuous functions of the controls that you're applying to it. So when you have a single quantum switch can be 0 or 1, when you measure it, before you measure it, there's an uncountably infinite number of states it can be in. It can be an arbitrary superposition of 0 and 1. When you measure it, you get 0 or you get 1, and you can bias the odds one way or the other by changing the probability amplitudes. So quantum switches are this weird mixture of analog and binary side by side. So when you want to think of a universal way of generating quantum statistics over binary digits, you need something like a circuit theory where I can combine 1 and 2 qubit devices in endlessly different combinations in different ways, such that I can make the output statistics to be anything I want consistent with quantum physics. So a quantum circuit is this abstraction. It's based on qubits. That is, quantum systems that can either be in one of two states, and when you measure it, you get 1 bit. Gates, which are simple ways of forcing control collisions between qubits to enable them to become correlated. And circuits, which are sequences of synchronized operations of qubits colliding with qubits and qubits undergoing independent manipulations. It's an easy fit because typically quantum mechanics is written in terms of Hamiltonians. Schrodinger's equation tells you if you want to calculate the probability amplitude of a particle to be at point x at time t, write down the Hamiltonian, solve Schrodinger's equation, and you're done. But that's a continuous equation in time and space. To discretize it, you have to make a little trick. You have to turn what's an evolution under Hamiltonian into some sort of discrete gate-like evolution from before the gate to after the gate in terms of a scattering matrix. Think of it as a control collision rather than interaction. All you really care about is what went in and what comes out. So that's called trotterization, but this is getting technical. Basically, this abstraction of qubit gate circuits was a good way to come up with all the different ways you could generate arbitrary probability distribution over n qubits. So that's what a quantum circuit is. In the same way that a classical Boolean circuit generates all classical probability distributions over binary numbers, a quantum circuit generates all classical measurement outcomes over binary quantum objects.
So, quantum learning machine.
Okay.
Tell us, enlighten us.
So it's early days yet, and many different directions are being pursued. One direction is, to some extent, learning could be considered as part of feedback control. Basically, you have a signal, which you label in some way. You put it into a machine and the signal gets distorted. But you want to be able to distort it in such a way that one kind of signal will be distorted distinguishably from another kind of signal. And the way that's done is by you keep measuring and feeding back. So let me give you an analogy. Imagine that there's some farmer who has a field full of sheep and goats, and come time to send them off to, their inevitable demise, you have to sort the sheep from the goats. And you could just go in there to the paddock and pick up a sheep and take it to one pen and pick up a goat and take it to the other pen. That's a lot of work. Imagine you try to build an automated process that will do this so that sheep and goats will go in randomly at one end, and there'll be a bunch of pulleys and ramps and gates and spring-loaded mechanisms and goodness knows what, which then puts sheep out one exit and goats out the other. But initially, it doesn't do anything other than random. So initially you started off in some arbitrary configuration, this complicated machine, and you put a sheep and a goat at random in one end, and the sheep is just as likely to come out the goat exit as the goat is just as likely to come out the sheep exit. But now what you do is the following. Every time an animal comes out the wrong exit, you go back and you can change the setting inside the machine. You tighten up some spring, or you close the gate. And all of those are irreversible processes. They have to, have to be enough friction so you can change the machine irreversibly. Then you run it again. And you keep doing this over and over again until almost always sheep come out in the sheep exit and goats come out in the goat exit. There's always some small probability of error, but you can get it down low enough if you try hard enough. And fundamentally, what you've been doing is making measurements on whether the animal is a sheep or a goat and changing the configuration of the machine through feedback. So that's essentially what learning is. This machine now will classify four-legged sort of hairy bipeds either as a sheep or a goat, and the farmer doesn't have to intervene at all. One important point to note there is that the machine is highly irreversible. It has to be, because initially you had high entropy, a random assortment of sheep and goats, but after you've finished, the sheep are on one side and the goats on the other mostly, and so the entropy has clearly gone down. And so you're paid a considerable heat price in setting the machine to do that. So you can think of learning as a kind of feedback control where you make measurements and you keep changing the setting of the machine so to get the right measurement outcomes you want. Now you can think of a quantum machine learning as a bit like that. It's a kind of very complicated feedback control process where you have a way of putting in quantum states that may encode different classical information. It may turn out that you encode all the sheep as wave functions located to the left of the origin and all the goats as wave functions located to the right of the origin. And inside there you have a quantum computer which has lots of settings, and you run it through and you measure it, and depending on what you measure you go back and change the settings in the quantum computer. And you can set that up as a machine learning protocol. And so basically it's a way of generating probability transformations by using quantum mechanics to adjust the probabilities in the same way that classical machine learning changes probability distributions by adjusting settings in a classical computer.
And this will make learning much more efficient.
That's our hope. Yes, we believe that there will be more efficient learning protocols. And there may be a bit more to it than efficient. There may be there's this question of expressivity. And that is, if you build a classical machine to transform one probability distribution into another, you have to make certain that the thing you're trying to learn can be distinguished within that class of probability distributions. So you have to make certain that there's enough variability in how you can transform distributions that you can learn some function. And in deep neural networks, this is done by just putting in enough parameters into the model. In the quantum case, it may well be that the sort of distributions that quantum mechanics can exhibit violate Bell inequalities, all sorts of other weird and wonderful higher order correlation functions, may give you the ability to express functions more compactly than you might otherwise do, just because quantum distributions are of a different character to classical probability distributions.
Expressivity. I still understand what it means. Why did they choose this word?
Actually, it's not a word I chose. It's a word that's used in the machine learning community. It's somewhat ambiguous, but the key is let's take an example of pictures of dogs and cats. So dogs and cats are recorded on a digital camera. You have this massive array of pixels which record information about color and intensity and all the rest of it. If you just looked at the distribution of, say, intensity on there, they both look pretty much the same. They sort of fluctuate a bit. And if I just looked at them one after another, it just looks pretty random. But somewhere in there is the correlations between different pixels that really matter as to whether or not it's a picture of a cat or a picture of a dog. So what you need to be able to do is take those correlations, which in the raw picture are spread out all over the place, and force them into very characteristic output distributions that says, if the correlations are dog-like, the distribution will be bunched up over here, and if the correlations are cat-like, the distributions will be bunched up over there. It could be that you just don't have enough control in your classical learning machine. The correlations are just too complex to simplify into a simple classification like that. the miracle is we can do it, right? That if you're clever enough, you can build a deep learning network that will do it. With huge numbers of parameters and many, many steps. So the hope is that quantum mechanics may enable us to encode interesting correlations more efficiently. That's what I mean by expressive.
I see. So we're coming towards the end of the more strenuous bit for the listeners. I'll ask you slowly some more relaxed questions. You mentioned you were associated with something with philosophy of physics.
Oh, yes.
Or before we started the podcast, guys, we talked a little bit. And can you expand a little bit on that?
Sure. So this is in collaboration with two colleagues of mine at the University of Queensland. One is Pete Evans in philosophy, and the other is Sally Shrapnel in physics. And Pete is a philosopher of physics. He's been interested in all these measurement problems and other things that have been around a long time. And we discussed the role of the observer earlier on, and I pointed out that you could get rid of a human observer and automate everything. The problem doesn't go away. So the philosophical question is, how do all these problems of the interpretation of quantum mechanics look now in the light of automated learning? Do we have a clearer view of what an observer is once we understand the role of learning in ordinary everyday physics? One example of this is connected to a problem called Wigner's friend. So in Wigner's friend, two different observers can have a completely different description of the quantum dynamics depending on what observables they have access to. The way it's usually described is a bit of a bait and switch, because Wigner and his friends of one sort or another are supposed to be complex, rational agents that can learn and experience and all the rest of it. When you actually look at the experiments, they're done with 2 or 3 photons. But anyway, that's a whole other story. But in the setting of machine learning, Wigner's friend is really a problem in multi-agent learning. So we know there are many situations where you might want different learning machines making observations on the same piece of the world or the same database. And in order to form an understanding of the correlations, they have to be able to share information amongst themselves. This is an acute problem now with the whole agentic drive in AI. We have all these bits of code running around trying to do stuff. Agent A could wipe out what Agent B does unless they have some shared protocol about what they're trying to achieve. So multi-agent learning is precisely the setting that would be useful for understanding many quantum paradoxes, such as Wigner's friend, such as where objectivity arises. Does it arise only when different agents combine different perspectives of the quantum world? And so you can see pretty clearly, I think, that many of the classical problems associated with quantum foundations look quite different once you understand how machine learning works. I sometimes like to call this, this is the question of whether do quantum androids dream of electric cats? I don't know if you've come across the old novel, well, it's a novella by Philip K. Dick called Do Androids Dream of Electric Sheep? It was the basis of the movie Blade Runner. The idea being that it's only humans that dream of electric sheep. Maybe androids don't. So I was being a little bit flippant by saying, do quantum androids dream of electric cats? Because certainly humans dream of quantum cats all the time. And so you might say, well, if I had a fully automated quantum laboratory, discovering new rules of quantum physics and happily engineering new materials on the basis of that, is it going to get hung up on the interpretation of quantum mechanics? Does it care? Well, it just does what it does. Maybe it'll get to the point where it can't understand classical mechanics after a while. If it has, arguments over the interpretation of classical mechanics, because it never sees classical mechanics, it just sees quantum mechanics. So that's one aspect of this philosophical problem. I mentioned earlier, I'm very interested in understanding clocks and how to build clocks and what time means. Philosophers have been arguing about time forever. Well, at least since it's the Greeks anyway. But time in quantum mechanics and understanding of quantum clocks gives you a different perspective on what time should be in a philosophical setting.
What's your work on clocks? And talk to us a little bit about the philosophy around time in
Sure.
physics.
Okay, so the first thing to be clear about time is that it's very much a relational quantity in the sense that temperature is relational. When I say two things at the same temperature, it's more about a relationship between those two objects. If I put them together, heat won't flow from one to the other on average. Now, time or clocks, in fact, let's talk about clocks first. Let's put time aside for the moment. What are clocks for? Clocks are used for coordinating local coincidences between measurement results. So, for example, if I have a bunch of clocks in this room, each sort of ticking away, and let's imagine they're digital clocks, just counting 1, 2, 3, 4, 5. They may be slightly out of sync with each other, doesn't matter. I can sit here pressing a key of middle C at sort of random times, and every time I press the key of middle C, I make a note of the reading on a clock. Or if I have a particle that's oscillating backwards and forwards, and every time it passes a certain point, it rings a bell, I could listen to the bell and record an integer on the clock. If I bore a big table of clock number, clock count, 1, 2, 3, 4, 5, 6, in the left column, and in the right column, I put a 0 or a 1, depending on whether or not I heard a bell sound. And I have this massive table, and there's no more physics left in the description of this problem than is in that table. It's a large collection of coincidences between count on the clock and 0 or 1, did I hear the bell or not? So essentially I have a function, a integer valued function of binary numbers, or a binary valued function of integer numbers, if you want to do it that way around. Where's time in this picture? Where's little t? Where's this real number that we all think of as time flowing uniformly? It's not there at all. There's nothing more in that experiment than that list of numbers. It just turns out, because of some beautiful theorems in integer functions, that I can write all the contents of that table in terms of what's called a real parameterization. Instead of writing a table of n and a binary number, if I hear a bell or not at that count, I can write n as a function of t, where t is a real number, and the binary number is a function of t, where t is a real number, and I can completely represent that table in terms of that real number t. But it's not physical. It's just a mathematical trick. But if I don't choose a good parameterization, it will begin to distort what's already implicit in the table. So there are good representations and bad parametric representations. But that's what we do in physics. All of physics, the equations we write down are written in terms of an arbitrary real parameter called t. It's not time. What time is the correlations between measurement results. It's an old point that goes back to
The last thing that time is the last sentence is that
the little parameter t,
yeah.
the real number t, is not time. It's just a mathematical trick to represent the relationship between coincidences. That is, did A coincide here and now with B or not?
I see.
So in this sense, clocks coordinate local coincidences, and what we regard as time is some abstraction based on the fact that things change locally. But the little t that appears in the equations of physics is not time. It's a mathematical trick for keeping track of all the correlations between local coincidences. And this is written into the core of general relativity. This is the idea behind general relativity. It doesn't depend on the coordinate systems. What matters is what is the gravitational field when near where two particles collide, or something along those lines. So general relativity takes it to the extreme. Not only is little t physically meaningless, x, y, and z are too. The spatial coordinates, what matters are all the coincidences between the physical events that are going on in the local region where you're doing the experiment.
Can you expand a little bit on the latter? So also x, y, z, you said.
In general relativity, the whole point of Einstein's theory of general relativity is it doesn't matter what coordinate system you choose, you can still write the equations of motion in a form that all observers will accept are correct. Now, it's based, in the case of general relativity, I have to just explain one further thing. The physical thing that means something in general relativity is what's called the invariant interval between two events. So if I'm looking at some region of space and time and I see two events, and because of my local coordinate system, they happen in different places and at different times, if I can compute the square of their separation in time minus the square of their separation in space, that is a number that all observers will agree on no matter what coordinate system they wish to choose. So the way general relativity works is it enables you to pick any coordinate system you like and then start making measurements of the invariant interval between events. They have to be really close together, infinitesimally close together, and make a big list of all those invariant intervals, and that is the gravitational field. The gravitational field determines what all those invariant intervals are. So one way to think about it is if I'm just using quantum fields and I want to measure gravity, I have to have a source and a detector, and I have to be able to propagate the field from source to detector. And on the basis of counting of detection events, I can back out what the invariant interval was between source and detector. And that will depend on the gravitational field in the vicinity of the source and detector in often pretty complicated way. So the physical fact is the metric. It's the physical thing that requires you to make measurements. That's the invariant interval between two events. We call it the metric. The x and the t, the x, y, and z, the coordinates we choose are completely irrelevant. Now, you may make life hard for yourself if you choose an unwieldy coordinate system. And in fact, you may make life so hard for yourself that you mistake mathematical artifacts of the coordinate system for real physical effects. But at the end of the day, once you can write it in a form that doesn't depend on the coordinate system, which is precisely what general relativity is, then you can make statements about what the actual physics is that's going on.
So how, if at all, has your everyday view of the world changed over the decades when working in
That's
this
an interesting
field?
question. Quantum mechanics came as the biggest shock, I suppose, in my second year when it finally hit me what the theory was saying about the world. I found it deeply disturbing. It begins to raise questions about, as we all know, between subjectivity and objectivity, between what Thomas Nagel called the view from nowhere and what I like to call the view from somewhere. But the biggest change since then, and how old was I when that happened, 19 or something, 18 or 19? The biggest shock came when it finally dawned on me what machine learning was all about. That what's sitting between our ears is a machine that is a physical device used to compress experience into forms that make it easy for us to respond to the world and control the world. Once you get the message of machine learning, all of physics begins to look very different. In fact, the notion of truth becomes problematic. It already was problematic, I suppose, but and you could imagine a situation where different sorts of machines enabled with different actuators and different sensors, different affordances, might learn completely different ways of compressing their experience, by which I mean completely different laws of physics. You could imagine some machine evolving in a region of the universe where instead of things changing on milliseconds, change on nanoseconds. What sort of universe does that machine see? What sort of laws of physics does it describe? Would we be ever able to communicate with it? Would we even see it? Or the converse, what if the fundamental timescale of the physical learning machine was millions of years? Would we ever recognize it? Could we ever see it? Could we ever talk to it? Almost certainly not. So these ideas have been out there in science fiction for decades. But once you get the message that machines can learn, that they can reconfigure their internal states on the basis of experience in order to control the world more effectively, the whole business of physics begins to look somewhat different to what it did when I was 17 or 18.
Interesting. So this might be stupid, so it's a disclaimer, but if so the way if the hardware, let's say we humans have our brain as the hardware of that compresses this information and makes us experience the world some way. If that hardware changes, does that bias us to come up with certain theories? But if the hardware was different, would it bias that other hypothetical species to?
Precisely.
Yeah.
That's the question. So it goes back to Kant, who
Critical Kyrry.
Immanuel Kant, the
Yes.
philosopher, who says we can never know the thing in itself.
Yeah, I read his Critical Kyrry. Tough book to read, but it also reminded me of that. It's like our biological limitations.
I leave Kant to my philosopher friends, but occasionally we talk about these things. The notion that, it may well be that in biological agents, the way they're physically embodied really does matter a lot. It may be that LLMs is just the tip of the iceberg. Things that manipulate language may be not the most fundamental way in which things can learn, and the way in which things can learn depends on how they're embodied in the world. That idea has been around in philosophy for ages. It goes back to the existentialists and Merleau-Ponty in the French tradition. And maybe as we move towards so-called world models and physical models for AI, when we build robots, we'll become quite open to the idea that the kinds of things we learn depend on how we're embodied in some very important sense.
I have to remember to ask you to send me your friends' emails. I want to talk to them about that. Is there anything today we haven't talked about that you'd like to talk about? We definitely have. What's we're closing to the end now? What's one thing that you'd, I guess, suggest to someone that's thinking of entering the field of physics but is unsure?
Right. Well, that's a question I'm asked a lot. The first thing is you have to be pretty passionate about these sorts of questions. You have to really, in some sense, need to do physics and mathematics, not just want to do it. It should be an internal compulsion that you find deeply satisfying and deeply unsatisfying if you're thwarted in your attempt. The other key things I'd emphasize today is get extremely good mathematical grounding. Make sure you understand coding and computer science and so on, and make sure you spend some time in a laboratory, because it's the laboratory experience, I think. Now, I'm a theoretician. My life in the laboratory was distinctly unsuccessful as an undergraduate, but I've always maintained a close link with experimentalists, and I think it's very important to maintain that link, to keep in mind that physics is all about the world and how we experience it, not just the mathematical theories we use to describe it.
How was your time in the podcast? How did you enjoy it?
Good. Yeah, it was fun. It was very enjoyable. Very sensible questions. I probably talked too much.
No, it's
Interrupted me a little bit more. But
no. This is great. I don't like interrupting
yeah, it was great.
my guests, because I was talking to Professor York about it too. I think people, when they feel comfortable that they can express themselves without someone rushing them, they take their time, they make their arguments a lot more coherent, structured, and a lot of the time you get really solid, valuable information.
That was great. I enjoyed your questions. They were asked at just the right moment to clarify things, so that's good.
I'm happy about that. My last question, which is the same I ask to everyone, is if you had to summarize your life's mission in one sentence, what would that sentence be?
Yeah. It's all about making sense, I suppose. Does it make sense? Is it all just random, or is there some deep structure to experience?
Thank you so much.
Okay.
It was a pleasure to have you on the podcast. I really appreciate you taking the
Yeah.
time
I enjoyed it.
to have the conversation. And guys, we'll see you at the next episode. Peace. Thank you so much, sir.
Thank you.
I feel bad because I forgot to say thank you in the beginning too, but
Oh,
at least I heard it. It's
does the other you put it in?